Where we are at in the process, Dr. Hoodbhoy, is these guys have put together three different proposals now, and the idea was to explore multiple themes before we kind of narrow onto one or two themes that we would like to submit to CERN. The closing date is April 10th, so I'm hoping by this Sunday with this session and a couple of other sessions with, we have a session with Rizwan Khalid and Sabi Anwar, etc. So by Sunday, this group will be able to decide whether they want to pursue one theme or at most two out of these three themes. And then
Okay.
from 1st April till 10th April, they will begin perfecting the final proposals as they will go in. Uh, Ideally, I would like you to be, this is obviously an interactive session. I think eight of them are here. A couple more will probably join sooner. So ideally, I would like you to be as critical. I hope the kids will not mind if Dr. Hoodbhoy is a bit critical of the proposal. So I would rather that we hear the wrongs in the proposal today than we either hear them at CERN or not hear them at all, right? So obviously we would love for your feedback and some constructive suggestions on how to improve it. But if there is something that is glaringly wrong in any one of those three proposals, we would rather hear from you today rather than hear from somebody else later. So with that, I'd hand over to you. There are three proposals. I don't know which way you want to run this session, whether you want to go through them one by one. There are multiple people here who have kind of authored those three proposals. So when you go through a proposal, we'll ask the right person to respond and interact, etc.
Right, right. I get the picture. So I am looking into the camera, right?
Yes, you are.
Okay, good. I received 4 proposals from you, of which 2 have been joined together. And just before coming here to the black hole, 15 minutes earlier, I got another proposal, but I haven't had time to look at that. So I'll concentrate on just the first 3. In terms of being critical, no, that is not my intention. But I think we need to see what are actually interesting and possible experiments which can be done at this BL4S or whatever at CERN. And certainly, one has to look at it with the eye of objectivity. So let me look at the first proposal which you had sent me. It is now joined up with the 4th one, and it is titled Measuring the Magnetic Moments of Kaons Using a Klystron and Dipole Magnets. And it's several pages, and I don't plan to show it because right now we're not connected. So here we must actually begin with the physics. After all, you guys are going there now to do physics experiments, and so the physics ought to be very clear to you. And the very first question is, what is a magnetic moment? Well, if there's a ball of charge, and that ball of charge is spinning, then because it spins, it creates an electric current. Now, wherever there's an electric current, there is going to be a magnetic field associated with that. And because some charged elementary particles spin, therefore they have magnetic moments. Now, यार ये जरा साफ कर दो इधर, हाँ. So, the electron has a magnetic moment. The proton has a magnetic moment. But it is not really necessary that that the particle have the particle can have net zero charge like the neutron, but it's not neutral everywhere. There's more charge inside the neutron than there is outside, because the neutron is a composite particle. So when a neutron spins, even though it is neutral, it still has a magnetic moment. Now, even particles which are called mesons can have magnetic moments. So for example, the rho meson, which is made up of U and U bar quarks, does have a magnetic moment, but unfortunately, this is slightly unfortunate, the kaon does not spin. The kaon does not have a magnetic moment, so you can't measure it. And so therefore, proposal 1 and 4 simply will not fly. You see, you guys could have simply Googled or asked ChatGPT, has the magnetic moment of the kaon been measured? And you'll get the answer, no. Then you could have looked at as to why it doesn't have a magnetic moment, and somewhere along the line you would have been told that it doesn't spin and so can't have one. Okay, so that's a bit discouraging. But let me say, there's still stuff that you can do which is interesting. Given that CERN is going to provide you a beam of particles which includes protons, electrons, muons, and other particles that spin. And all these magnetic moments are very well measured. So if you simply go and tell them, hey, we're coming to measure the magnetic moment of the electron, well, that's been measured better than any other quantity in physics. In fact, up till 14 places of decimals. So they'll say, thank you, but go elsewhere. So what is it that you can do which is interesting? And here is something that I'll propose to you. You've all heard of nuclear magnetic resonance. So basically, before we get into more of this, here is how you write the magnetic moment. So the magnetic moment is actually a vector. It points somewhere. It's written this way, E over 2 times the mass of the part. E is the charge of the particle. M is the mass of the particle. And there's a factor called the G factor, which I won't write. G is equal to 2. And it points in the direction of the spin. So this should tell you that if there's nothing spinning, there's no magnetic moment. Okay, next point. Let's take a particle which is spinning, so like the proton, the muon, the electron, and many others. Now these guys are spinning, they have magnetic moments, and if you put them in a magnetic field, then if you put, let's say the magnetic field is pointing up like this, well then if a magnetic moment points this way, it gains some energy. If it points this way, it loses energy. And there's a difference of energies between a particle pointing up and a particle pointing down, that is to say, relative to the magnetic field. Okay, now in quantum mechanics, that means that particle is actually precessing. Precessing means it's going around an axis, round and round like this. So and it precesses at a rate, at a frequency, which is called the Larmor frequency. And that frequency is the charge into the magnetic field divided by mc. So the bigger the magnetic field, the faster it precesses. And if you look at NMR machines or the kind of CT scan machines, not CT scan, what's that thing called? MRI, MRI जो अस्पतालों में होता ना, हाँ, MRI. MRI is actually NMR, but people are afraid of the word nuclear, so they call it MRI. Okay, so you have precession, Larmor precession. But what is this formula, when is this formula relevant? It's relevant when this proton or this electron or this muon is at rest. Okay, but then here is the situation that you are being given a proton beam which is not at rest, which is moving close to the speed of light. So if it has energy 10 GeV, that's roughly 10 times greater than its rest mass, and so it's highly relativistic. What did Einstein tell us about relativity? That when something is moving fast, it will appear to us that the clock that is moving with that is running slow. Okay, so here is a possibility for you to test time dilation using the proton beam which you will have and using a klystron. So you see, I'm trying to build on what you wrote to me, what you sent me, where you have a magnetic field. That magnetic field comes from a CERN magnet, and you have a klystron which will provide you radio frequency. Okay, but now see what I'm trying to propose. So here is the magnetic field going up like this. Here is your proton beam coming. This beam is going to make it bend like this. Now, in here, there is also the radio frequency, the microwave that the klystron has produced. Now, imagine that you're sitting on this proton. And now you're seeing this electromagnetic wave or this electromagnetic field rush towards you. Well, this is the first thing that Einstein had computed. It's called the relativistic Doppler shift. So you've all heard of the Doppler shift with sound, but there's a Doppler shift associated with time dilation as well. So basically, you see the clock, the fast-moving clock as running slow. What happens here is that this is being diverted. This is going in an arc like this. It's seeing an electromagnetic field, but not the same electromagnetic field that we are seeing. It's seeing a different field, and it's going to see a different frequency. So this might be something interesting. In fact, this is something interesting. How does the clock on a particle slow down as viewed by us? Not according to the person moving with the particle, but we who are in the lab. How do we see that clock being affected? So investigate the Doppler effect, and you can do it with protons, electrons, muons, anything that has a magnetic field, and also whose Larmor frequency is accessible. So it depends on the strength of the magnet that you have, but I think that something like 1 or 2 Tesla ought to be good enough for this. So it's not something that nobody has done before. You will not be doing new physics, but something is going on. हाँ, उनको म्यूट करना होगा. अच्छा.
Sorry.
Right, so I'm done with proposal number 1. And there are 2 more proposals. And then we'll have Q&A. Let me open the second proposal. So the second proposal is, it's titled Angular Distribution of Channeled Protons Through Bent Crystals. And they want to examine the dependence on bend angle and beam energy. So for the benefit of those who have not seen this proposal, the idea is the following. That you have a chain of atoms, and well, these produce a potential, an electrostatic potential. And normally, if you take a beam of particles and you hit it at a material, then it goes and it strikes an atom, gets deflected, undergoes large angle deflection, and in a very short distance, the beam gets totally spread out and loses energy. However, if you send your beam through, if you aim your beam right, and this is a crystalline structure, then it could be that a proton, or and usually this works better for positive charges, a proton will get repelled by the protons over here and by the protons here. And so these protons will then move along this sort of pipe. So you can think of this as like a gutter pipe, है ना, जहाँ पानी बह जाता. So these protons will then move along in that channel. And so this is what is called channeling. It was discovered some 30 years ago that some materials will allow for channeling. And it could be useful. It is useful, in fact, because you can take this chain of atoms and actually bend it around. So the proposal here is to have a bent chain of atoms. This is, of course, exaggerated. You can't bend it all that much. But if that happens, then the beam can also be bent. And that has certain benefits, like you can aim your protons, let's say, onto a cancer and destroy the tumor, or you could use it for lithography, which means deposit atoms at the right places in a lattice, various other uses. And so therefore, this is something very worth investigating. And so the people who have suggested it, they have I can't read the proposal over here, but it's fine. The thing, wait a minute, this is not going ahead. Okay. Now, one thing I did not find over here was that it was not explicit enough, and it was not clear enough as to what materials would be used and what they aim to find. Because look, the fact is that channeling was discovered a while ago, and in fact even bent crystals are now used in places. In fact, at CERN, there's a proposal to use a bent crystal to extract protons from the LHC. Whether it ever works or not, I don't know, but certainly bent crystals are a possibility. But there, see, bending the crystal for extracting LHC protons would actually have some real good use over there. So think about that. What are you hoping to get by this channeling? What do you hope to do by getting these channeled protons? And I'd say it's pretty much only the protons that you'll be able to channel. Certainly it will not be electrons, and I don't know what other particles, depends on the beam composition. Neutrons certainly will not channel because they don't feel a potential. Now, one thing that I did think of, which could be helpful to you in making your proposal better, is that, look, do you see the similarity between this and this? Here the protons are moving in an arc. Why are they moving in an arc? Well, here there's a magnetic field, and so you have the V cross B, the Lorentz force. What about here? Well, it's actually very interesting, because if you look at electrodynamics, relativistic electrodynamics, in the presence of an electric plus magnetic field, it tells you how a particle will bend. In fact, how it will move, how its velocity will change, how its direction will change, and so forth. Okay, now, effectively, this particle is feeling a magnetic field. You'll ask, how is it possible? Because look, there's nothing moving over here. This source, this is a fixed atom. A fixed atom just has a fixed electric field. But here comes relativity. If there's a fixed electric field, if there's a fixed atom with a fixed electric field and I move, then I will see not just the electric field, I will see a magnetic field as well. And in fact, this is what led Maxwell 200 years ago to formulate his equations. Physically, you can understand this, because if I move, I will see this charge as moving. Here it is fixed in this lab, but I will see it as moving, and any charge that moves, well, that's a current. If there's a current, there's a magnetic field. And so this guy, this proton from LHC, from CERN, SPS actually, if this proton is moving, is going to see a magnetic field, not just an electric field, and it's going to bend like this. Okay, now, mathematically this is quite complicated, but people over the last 20, 30 years have looked at the trajectories of particles in electromagnetic fields, and it's a solved problem. I mean, it's a little tough. I mean, you guys are doing your A levels, and so you won't be able to understand the tensor calculus that goes into this, but that's okay. What you can do is calculate the effective magnetic field, which gives rise to this bending, and that by itself is interesting. It's actually much more interesting than just measuring the magnetic moment of this or that. So think about this. Okay, so I'm nearly done with proposal number 2. My suggestions are give some concrete reason why you're doing this channeling and this channeling experiment and more details of how you will do it. And then put this as a reason as well. This is a pretty strong reason to find the effective magnetic field experienced by a proton as it goes through a crystalline structure. It's not a trivial problem, this is a nice problem. Yes, and one last thing. If you need a reference on this, I can find one. Or you can find one. Go to lots of places now. You can go to Google Scholar, you can go to ChatGPT, whatever. But if you have difficulty in that, just write to me. I'll find a reference which will tell you how channeling has been looked at theoretically. You know, in our part of the world, everybody wants to do experiments, but they don't want to read the theory. And that's why we don't get ahead very far. First comes the theory, and then comes the experiment in any good experiment. So that's all for the second one. Third. So this is proposal number 3. The title of this is Shielding Against Solar Radiation and Cosmic Rays, Material Testing for Spacecraft Protection. Well, it's clearly very important. You have satellites in the sky which are constantly irradiated by solar radiation, by cosmic rays, all kinds of junk in the sky. And of course, this is just telling you what you know, that the sky is not empty. It's actually got a lot of stuff in it. And these satellites keep hitting this junk, and that's why they have a finite life. I don't know how long a typical satellite lasts, but not more than a few years. It takes many tens of millions of dollars to put it in space, but at the end, all this radiation kills it. What does it kill first? The electronics. Now the electronics, so all of this is semiconductor electronics, and so if a proton comes or an alpha particle comes from the sun and punches a hole through your memory chip, then it's not good for the memory chip. You lose that part of the memory chip. So therefore, shielding is very important. So I completely agree with the spirit of this proposal. However, you guys ought to know that already there is a lot of effort that has been put into developing radiation-protected materials, radiation-hardened materials into satellites. And this is done both commercially and in places like CERN. So let me tell you what I found is going on at CERN, which actually you should have looked at before making this proposal. So I went to the internet And here's what I found. I've just downloaded that. CERN has extensively explored radiation damage to materials due to high radiation levels present in its particle accelerators and experimental areas. At CERN, there are several, not one but several dedicated facilities that look at radiation damage to materials. One of these is called R2M, Radiation to Materials. And they tell you where it's located. There's another which is here. My cursor is, okay. There's another one which is called EAIRRAD. That's the proton irradiation facility. And they tell you it's located in the east area. The facility uses a proton beam to irradiate materials. There's a gamma ray irradiation facility. There's a facility that uses neutrons, a facility that looks at stuff that comes out from the accelerator without particularly caring what's there. And they test a very wide variety of materials. So I'll just read from the list. They test cables and wires, insulators for magnets, vacuum components, resins, optical fibers, electrical heaters, lubricants and greases. Greases are particularly important because when you go into space, you have all these relays and these mechanical parts, and there's grease over there. So when the protons and the alpha particles from the sun come and hit them, the grease stops working. Then you have mechanical friction, etc., etc. Now, your experiment does only this. You say, yeah, we have a beam. We're going to hit it with that beam is going to hit a target. We're going to see how much is reflected, how much is absorbed. But wait, that doesn't tell you anything. You have to see how much structural damage is done, whether the atoms are forced apart from each other, whether that electronic component is damaged to the point where it will cease functioning. And so this is a whole science which now commercial companies, they regularly practice. In fact, if you go to the net and you ask and you look around, you'll find private companies which will harden components that you want to send into space. So suppose you want to make ParkSat 3. I think the first two failed. You want to make ParkSat 3, all right? Which orbit are you going to put it in? They'll tell you, okay, you're going to have this sort of radiation coming onto it, and so you've got to protect it against that. They'll tell you the kind of materials that are available and so forth. So my point is that if you send in this proposal to CERN, they'll say, but guys, didn't you even look at what we at CERN are doing? We have facility after facility doing what you are proposing. So now I am through. On this proposal, I'll say, either you think of something different, or you should get more specific. There are ways in which you could get more specific, like you could say, I want to see how carbon nanotubes are affected, because carbon nanotubes are used in so many nanostructures now which are placed inside satellites. Of course, first you need to go to the literature. This is how to do science. You first search the literature. If you say that, I don't know what's out there in the literature, they'll say, go away. So first, search the literature. See whether somebody has actually done this work or not. Now, it may be that somebody has done the work, but if you can think of a better way of doing that, or you can think of a new twist, then people will take you seriously. So, I'm not a material scientist. I don't know very much about this, but my advice on this proposal is find something specific if you want to concentrate on material damage to satellites. Okay, so I think I'm done, and now I'll take your questions.
Okay, great. Thank you very much, Dr. Hoodbhoy. So, guys, if you can raise your hands so I can recognize you one by one. Maybe if you want to ask questions about the first proposal or the first proposition. फर्स्ट प्रपोजल किन लोगों का था? The magnetic moments one. Guys, questions? Safi, you were the... Yes, go ahead.
Sir, can you explain the theory and about the alternative experiment you suggested for proposal 1, and how can we do it in using experimental facilities?
भाई जो बताया उसमें क्या कमी रह गई? Tell me what you didn't understand about this proposal. What I'm saying is, one interesting thing would be to test out whether moving clocks run slow, whether time dilation is something that's real, and that you can do with a relativistic proton beam. इधर से 10 GeV के protons आ रहे हैं, इधर एक फिक्स्ड लैब क्लाइस्ट्रॉन है, क्लाइस्ट्रॉन से वेव्स निकलती हैं, मगर वो वेव्स निकलती हैं विथ रिस्पेक्ट टू द क्लाइस्ट्रॉन. क्लाइस्ट्रॉन लैब में साकिन है, खड़ा है. So here is a very nice situation to look at whether you will live longer if you go on a spacecraft and come back and have moved at the speed of light. तो अच्छी चीज है ना? It's interesting at least. It's better than saying I measured this and this and to 2 decimal places or 3 decimal places. At least there's something nice and conceptual about this.
So Dr. Hoodbhoy, how do you measure time dilation from the shift of the movement?
Okay. So you remember I wrote down the Larmor frequency.
I can understand you said कि इसके होने के लिए जरूरी है कि the particle needs to be at rest, right? So we are assuming from the perspective of the proton that it's at rest from its own perspective, right?
हाँ, बिल्कुल बिल्कुल जैसा कि अस्पतालों में होता है, मैग्नेटिक फील्ड आपकी मशीन के साथ लगा हुआ होता है. प्रोटॉन्स आपके जिस्म के अंदर हैं, आपका जिस्म भी साकिन है, उधर आप लेटे हुए हैं. अच्छा, तो वो तो सब एट रेस्ट है ना. अब ये स्पीड ऑफ लाइट से दौड़ता हुआ आ रहा है, तो फिर क्या होगा? अगर आइंस्टाइन की बात ठीक है, तो हमारे बकौल इसकी घड़ी सुस्त चल रही है, इसके बकौल हमारी घड़ियां सुस्त चल रही हैं. तो ये अच्छी बात, दिलचस्प बात बनती है ना. वैसे तो look, you will find a confirmation of the special theory of relativity, but at least it's nice. So now the question is, how will you find the conformation? Okay, this is the resonance frequency while at rest, but the resonance frequency when this is moving will be different. Now your klystron can be tuned. It can give radio frequency waves at this frequency or that or that. When the two frequencies match with each other, then you have up, down, flip. So this is how you will know that the two times are different. My time and the time of the person who is moving with the protons.
Okay, and for different sorts of particles, if the beam was comprising different sorts of particles, the shifts would be different, and that would give us different results for different particles?
Yeah, because you see they have different masses, for one thing. But the other thing is that it's speed which comes into Einstein's equations. It's velocity rather. And if there's a particle of the same energy, if there are two particles which have the same energy but one is heavier, then the heavier one is moving slower.
Okay. Any other questions, guys? Safi, any other questions on this, or anybody else from that group? Okay, I think we can move to the second proposal, perhaps. Second proposal किसका था? Danial, Abdullah, Majid, and Moiz. Guys, any questions about the second proposal?
Yes, I have a question.
Go ahead.
Dr. Hoodbhoy, yesterday I came across a paper which theoretically explored the channeling of 1 GeV protons in bent, very short, single-wall carbon nanotubes. And it's a very recent paper, and I saw that they concluded that the bending power of such crystals was greater than even the dipole magnets in the Large Hadron Collider. So, do you think this is an interesting idea to explore experimentally, as
Yes.
it hasn't been explored experimentally yet?
Now, see, I'm not an experimental particle physicist. I'm a theorist, but and channeling is something that I heard of 20 years ago. I haven't followed the field, but I can well imagine that what you're saying is true, because carbon nanotubes, they have these hexagonal structures and very regular ones, and these nanotubes can be quite long. So if there's a high energy proton beam, and by the way, the higher the energy, the better. That's because the particles are more localized. And so their impact parameters are controllable also. Okay, so yeah, I don't know what paper you're referring to, but it sounds interesting. And maybe you should think of the idea of doing this experiment with nanotubes. And carbon nanotubes now you can buy commercially. CERN will, I'm sure, get them for you.
Thank you.
Moiz, you want to ask something? You've written something in the chat. Why don't you ask?
Sir, I asked that, so using these carbon nanotubes, can we bend protons for smaller radii? Like you said, we can't do it for, we can't bend it a lot, like the arc is very exaggerated. So using carbon nanotubes, can we do it for smaller radii?
Small radii means more bending. Yeah, look, the more bend you can get, the better. See, think of the optical fiber that brings internet to your home. You can coil it up, but you can't make that radius too small, because then the critical angle gets exceeded and then the signal leaks out of the fiber. Similarly for the proton, if you can make a proton beam bend more in a smaller amount of space, that's so much better, because then you won't need a very long carbon nanotube. And nanotubes are, of course, they can't be too long. It's very hard to make them. The longer they are, the harder they are to make. So yeah, I think that would be, the ideal thing would be to have things that can just go back on themselves in the space of a few nanometers. But that's not going to happen, of course.
So Dr. Hoodbhoy, what is the deciding factor in the, what is the most critical factor in this? I mean, is this, if you want to bend something very in a short radius, either you have to reduce the speed or you have to
It's the
increase
angle. It's the angle of incidence. So suppose you have, let me illustrate this with water. So here is water, and here is air. So as a ray of light comes towards this, it will bend towards the normal, right? This angle over here is going to be smaller than this angle over here. It gets bent inwards. Now, imagine that I reduce this, imagine I bring this ray of light closer and closer. At one point, what will happen is that instead of going into the water, it will be reflected back. That's called total internal reflection. And this is what makes your optical fiber work. And this is why we want protons to be total internally reflected. Okay, it all depends on the critical angle. There's a critical angle after which total internal reflection takes place. If you exceed that, then it leaks out. It leaks out into the water.
No, so for this, I understand that, but for this crystals, atomic crystals,
Yeah.
you can't, are we going to change the angle at which the beam of protons hit these crystals?
Oh yeah, sure. That's exactly the point.
So we can't, I mean, we can't change we're going to change the direction of the beam, right?
You can change the direction of the beam, yeah. And see, here is one medium and here is another medium. This could be vacuum. Let's say this is vacuum and this is a medium. Now, for different media, you will have different critical angles. So that's why you see the optical fiber. If you open up a cable, you will see it is wrapped with some translucent material, and the choice of that material is very important. So there's the optical fiber inside, and they call it the cladding, yeah. Choice of cladding. So
Is it possible to slow down this beam? Is there any value in slowing down the beam?
oh sure, but it took so much effort to speed it up, I mean, those guys at LHC, they start with 14 tera electron volts, TeV. And that cost about $20 billion, more than that. By the time it comes down to the students who will be using it, it will have been degraded 10,000 times. And it'll become 10 GeV. So you don't want, you see, high energy proton beams, by the way, 10 GeV used to be the absolute limit 50 years ago. That was considered the highest of high energies. Now they're giving it to students.
So the trick is in the placement of these crystals.
The trick is choosing the right crystal, which has got, which will give you, see, it's like being able to punch a hole in the wall which is straight, but you can't do that. It has to be naturally arranged. This has to be a crystal which has been like rock salt. Rock salt is a crystal, natural crystal. Or you could use diamond. Diamond is good. Diamond will give you a very good channel.
But relative to the beam, don't we want the properties of these crystal atoms to be such that this channel is properly produced, right? What we are trying to measure is, I mean, in the language of this, the light example that you gave, you're trying to manage the properties of these two surfaces.
We're trying to find the place where there's a gutter. पानी उसमें से बह जाएगा ना, तो
No place where there is a gutter, but what you are able to manage is the material, but within the material you are trying to manage what kind of properties do these atoms have so that the ray passes through.
It's not the atoms, it's the crystal lattice. तो lattice को आप यूं देखें तो आपका बीम इसमें से गुजर नहीं सकेगा. इसको यूं कर लें और इधर छेद है तो ये उस छेद के थ्रू ऐसे गुजर जाएगा.
लेकिन हम इसको बेंड भी तो कर रहे हैं ना.
वो बेंड, हाँ, बट दैट्स एडियाबैटिकली. आहिस्ता आहिस्ता आप इसको मोड़ना है ना. You're bending this, and so the proton beam will follow.
So the atoms of the crystal are not interacting with the beam in any way.
They are.
Because I thought the atoms were interacting with the beam.
No, they are. If you take away these atoms, this will not bend. They are, but they're contributing their electric field. You see, this is a proton over here. This proton is repelling this proton here, but so is this proton repelling it. So this is a sort of this over here. Let's take this point over here. This proton is being pushed by this positive charge and by this positive charge, so it doesn't stray too much off the path.
So I'm just thinking that if we want to increase the bend, then we want the right levels of positive charges in these atoms to be able to bend it exactly the right amount so the light can pass through, the beam can pass through, right?
Yeah.
Okay. Any other questions, guys, about this? Okay, let's go to this.
Question.
Yeah, go ahead.
Could you kindly tell what is the significance of extracting the protons from the Large Hadron Colliders using bent crystals? Like, what can we do with those protons or things like that?
Look, I am just guessing. I don't know. But, the Large Hadron Collider, they don't even let you close to it because it's got so much synchrotron radiation that comes out of it. So it's 300 meters below the ground, and no humans go over there. Okay. Making any kind of a port over there. So the beam is going around. You can't just खिड़कियों से भी नहीं खोल सकते ना. There's superconducting magnets. There's all kinds of things over there, cryogenics, etc. So if there's a little opening that you can make, which is not going to disturb things too much, then there is definitely an advantage to that. But as you told me, this is just a proposal, and I don't know if CERN will approve it, or if it's worth approving. I have no idea. I have not seen the paper. Certainly, there would be an advantage to it, but that's obvious.
So there are specific points on the LHC where you can either place something active in there or
Only
stuff,
4,
right?
I think there are only 4 points.
Yes. So what you're saying is that beyond those 4 points, you can create other portals into the LHC, so you can draw out beams of whatever kinds you want to pull out, right?
Yeah, that would be the idea.
And the LHC, I mean, you can place stuff inside the, inside the channel wherever you want.
No. Only
No,
at these
right?
4
You can't.
places. No.
So there are certain places where you have those, where the collisions happen and where those
Yes.
detectors are and stuff. तो आपको वहीं से कहीं पे वहीं पे कोई चीज लगा के करनी है.
So it's 27 kilometers, and divide that by 4, so about little over 6 3/4 kilometers apart.
Sure, guys. Any other questions about this proposal, or should we move to the next one? ठीक है जी. I think let's move to the next, the final proposal. So the guys who were with the final proposal, I think Dr. Hoodbhoy said you need to make it more specific to make it more interesting. Ji Saim, go ahead.
Yes, so you said that we have to be more specific about it, what materials we are using. So I want to say that actually we are being specific. You mentioned about we are not just using some general materials which are already in use, such as titanium, such as MLI blankets. So we are actually using some special materials. You mentioned about carbon nanotubes. We have mentioned in the proposal boron nitride nanotubes, and being more specific, we will mention hydrogenated boron nitride nanotubes. So these are very lightweight materials. These are not very much used in satellites. They are not very common materials. And another one we have selenomanelin. It's actually a biomaterial. It's a biomaterial. It can be coated on the suits of astronauts. So these are some special materials. We are not just testing that any material. They have potential, but they are not very much used and very much tested. So I think that if we have opportunity, we can test these materials. And second thing is that we are not testing the whole electronics. So you said that in our experimental setup, some protons will just penetrate and some protons will be reflected. So we cannot.
No, I didn't say that. भाई मैंने ये कहा कि सैटेलाइट्स जब ऊपर होते हैं ना, सबसे ज़्यादा अंदेशा इसका होता कि सोलर रेडिएशन उसकी इलेक्ट्रॉनिक्स को तबाह करे. तो इलेक्ट्रॉनिक्स को शील्ड करना अशद ज़रूरी होता. मैं ये कह रहा था. ये नहीं कि आप CERN जाएंगे तो आपके इलेक्ट्रॉनिक्स पर उसका असर पड़ेगा. ना, वो मैंने नहीं कहा.
नहीं, आई एम रेफरिंग टू कि आपने कहा कि जब हमारा जो एक्सपेरिमेंटल सेटअप है,
नहीं, मैंने
तो उसमें जब
आपके एक्सपेरिमेंटल सेटअप की मैंने बात भी नहीं की. मैंने देखो दो बातें हैं. सबसे, क्योंकि ये एक ऐसा प्रपोजल है जो आप कहते हैं कि स्पेस के लिए है, सैटेलाइट्स को महफूज करने के लिए. तो ज़रा पहले ये देख लो कि आजकल सैटेलाइट्स को महफूज करने के लिए क्या क्या तरीक़े इस्तेमाल किए जाते हैं, क्या क्या मटीरियल्स और के मसले क्या हैं. जब तक आप उन मसाइल का अहाता नहीं करेंगे, उनको समझेंगे नहीं, तो लोग कहेंगे भाई ये तो खामखा एक मटेरियल बीम के सामने रख देता और फिर दूसरा रखता. तो इसका फ़ायदा किसको, किसी को नहीं होगा ना। तो अच्छा ये होगा कि पहले थोड़ी सी रिसर्च कर लो कि आजकल के हमारे तजर्बे में ये बात आई है कि फला फला मटेरियल्स जो इस्तेमाल होते हैं वो जल्दी गल सड़ जाते हैं जब उनको सैटेलाइट्स में रखा जाता है। बहुत कुछ लिटरेचर है, कोई एक सी चीज़ उसमें से उठाकर रख दो ताकि तुम्हारे प्रपोजल में थोड़ा सा वजन बने ना। तो ये एक दोस्ताना तजवीज़ है, अगर मुनासिब समझते तो करो, अगर नहीं तो ठीक है, नो प्रॉब्लम।
Saim, when you selected these two materials that you just mentioned, what was the reason you selected these materials?
I've actually researched about it and I read about it. There are some research papers where they said that there is potential. There is actually a professor, or I forgot the name, so I'll mention it. So he was researching on this selenomelanin. So when he researched about it, he actually developed this material and said that this material can be used again. It has potential of being used against solar radiation and solar winds. So that's why I said that if we can test this material at CERN, which some doctors say that it has potential, so it will be beneficial if we use these materials. So boron nitride tubes, they are actually being developed by NASA, boron nitride tubes which I'm mentioning. So I think that if we can mention it, test it at very, very high speeds. So these cannot be tested elsewhere at very, very high speeds, high energy protons. So if we can test these materials, which has potential, they are not just ordinary materials. So if we can test it, it would be beneficial. That's why.
भाई देखो, पहले ये जान लो कि जो नुकसान पहुंचता है प्रोटॉन्स की वजह से, अल्फा पार्टिकल्स की वजह से, न्यूट्रॉन्स और गामा रेज की वजह से, ये सारे मुख्तलिफ किस्म के डैमेजेस होते हैं। कुछ एटम्स के बीच में घुस जाते हैं, उनकी इंटरस्टेशियल डिस्टेंसेस बढ़ा देते हैं, कुछ एटम्स को उड़ा देते हैं, कुछ आयनाइज कर देते हैं, तरह तरह की ख़राबियाँ इससे पैदा होती हैं। तो इसको बहुत अच्छी तरह से कैटेगराइज किया गया, इसके बारे में थोड़ा सा जानना ज़रूरी है। अब आप कहते हैं कि सोलर रेडिएशन से महफूज करना, व्हाट एग्जैक्टली डू यू मीन बाय दैट? आर यू लुकिंग एट सम मैकेनिकल प्रॉपर्टीज, सम थर्मल प्रॉपर्टीज, सम इलेक्ट्रिकल प्रॉपर्टी? तो ये तमाम चीज़ें जो है ना, थोड़ा सा अपने प्रपोजल को मजबूत करने के लिए इनका जिक्र करो कि वी आर इन्वेस्टिगेटिंग दिस प्रॉपर्टी, वी आर इन्वेस्टिगेटिंग हाउ this kind of radiation, proton radiation for example, is going to affect this property of that material. तो इस लिहाज से इसको ज़्यादा specific बनाने की ज़रूरत है।
And if you are, as you said, if you are focusing on something that people find is not being addressed currently,
वो तो
then
और
it
भी
would
अच्छी
be
बात है,
more useful.
वो तो और भी अच्छी बात है।
You know, maybe, I don't know, I'm sure there are people who are already working on ये जो आपने biomaterial की बात की, so something to address long term radiations on suits, on space suits in Mars. You know, something like that would be of interest to people.
Sure, lots of
If it
things
is not,
can be of
if it is
interest.
not already being done. Yeah.
Yeah, lots of things can be of interest, just be more specific.
Sir, what would you advise that if we use one material or several targets, should we stick to one material?
I can't say anything. It depends what you want to do with that material, how many different properties of that material, how many different ranges of energies you're going to use, which particles. So this is just one variable of so many.
So So Dr. Hoodbhoy, any general comments about? I mean, I think what they're most of the proposals kind of are slightly struggling with is why is this an interesting question,
तो
right? उसके ऊपर कुछ
देखिए
suggestions होंगी general आप.
मेरा ख्याल है अगले साल के लिए, इस साल चलिए शायद कोई इनमें से लग जाए, उम्मीद करता हूँ कि लग जाए। अगले साल के लिए ऐसे है कि अगर कुछ 3-4 महीने पहले इस पर बात हो तो बेहतर होगा, ताकि स्टूडेंट्स फिर उस पर कुछ वक्त लगा सकें, कुछ रिसर्च कर सकें। देखें, मेरे नुक्ता नज़र से इसका जो असल फ़ायदा है वो ये कि इस तरह से इनको ज़्यादा फिज़िक्स सीखने को मिलती है। अब अगर वो बाहर जाने में कामयाब नहीं भी होते, और 10 में से 2 होते होंगे जो भी, लेकिन अगर इससे फिज़िक्स की समझ इनकी बढ़ती है तो फिर मेरा ख्याल है ये सबसे अच्छी बात है। तो मेरी तजवीज़ ये कि अगले साल कुछ 3-4 महीने पहले ये सिलसिला शुरू किया जाए। अब तो 10 अप्रैल को इनको सबमिट करना है।
ठीक है. Anything else, guys? Any other questions before we close the session? No questions. So we'll do another couple of rounds with a couple of other people, and we are trying to by Sunday evening we can decide upon which proposal to drop and which proposal to work further on and try to improve it and further cement it.
ठीक.
ठीक है. Thank you very much, Dr. Hoodbhoy. Thank you for your time. Really appreciate it, and I hope the kids would have found it useful as well. And inshallah, we'll try to do something more substantive next time.
Okay, good.